Now I will move to some example. I would like to show you in detail now some example. First on datation and dosimetry, and second part on persistent luminescence and afterglow. So datation and dosimetry. Dosimetry, everyone is familiar with that. If you are doing some X-ray diffraction, for instance, you are supposed to have a dosimeter close to the apparatus. And this is controlled every month or something like that. And if you are working with a high energy level, you have to control your irradiation. Datation is, for instance, a use to have some age of unknown material. So I will focus a little bit more on this part because it's interesting and not well known, I guess, for most of you. And the key point for the datation is that you will use by a solid has been irradiated with a dose Q0 during a time t. You don't know the time t, it will be the age of the material. So you have the number of traps, and you should use a calibration. Very important is the calibration. Then you know approximately the concentration of traps corresponding to a received dose. And you have the radiation time in laboratory, the source, in comparison to what was you wanted to observe. This is the dose received by the object that you want to determine the age. And this is the time. And you just have to divide. So this is called paleodose. This is the dose received by the object during all the years that he stay within a space. So, for instance, if you put something in this room, an object in this room, you cook something. For instance, you cook a pottery in the room. And if you keep the pottery in the room for several hundred or thousand of years, the pottery will accumulate the ambient radiation, and you can follow in case of deep traps, you can release the trap by heating the pottery and to know its age. So if you know the annual dose, the age is the dose that was trapped in the material divided by the annual dose. This is the calibration over there. So this is another way to present. You have the intensity. For instance, natural mineral, irradiation over millions of years. The traps should be empty for the T0. Very important is the T0. That's why, in general, we are using that for pottery. Because the pottery, you put the pottery in the furnace. That was done for, in the past, 2,000 years ago, they were doing the same kind of pottery. They did a fire, and they put the pottery in the furnace. It was a T0. At that time, all the traps coming from the raw material were released. So when they are cooking the pottery for the first time, it's a T0, it's the beginning. And then, during, for instance, during several thousand years, there is a natural radiation, and there is an increasing number of traps. And then you can measure the traps by thermoluminescence. Thermoluminescence, you release all the traps. You put your material in the furnace of the thermoluminescent setup, and you control the quantity of photon coming out, and it can be double checked by up here, the quantity. And you have information about the time and the datation. So this is the way to do this. So some example, of course, very important is to know the natural irradiation of the. This is not so easy, and you have to control this. For instance, if you can find a pottery around here, you need to control also what is the natural dose. So this is this red peak show you the natural irradiation. This is the peak coming from energy, spatial energy, and you have an information about natural irradiation around the surrounding of the place where they discover the pottery or something like that. So you measure So another example of natural irradiation. This is, for instance, you can simulate the, for instance, 72 hours of environmental radiation here, and 15 hours. And this is a calibration dose, for instance, corresponding to this 43 microgray of irradiation. So you can do some kind of irradiation like that, artificial irradiation, to approximately know what was the environmental irradiation. In the lab, you can try to simulate the radiation coming out from the field, from the exact field. So, first example that I want to show you, in the Louvre there is a lot of pottery like that. They are coming from this part. I think I have another one. Okay, this part of Greece, Tanagra. So it's approximately 53 kilometers from Athens. So you see, it's not the Shinkansen. 53 kilometers, 1 hour 14 minutes, because the road in Greece are very narrow, and you cannot go very quickly. So if you look at this pottery, very famous pottery, they were painted and they were made between 300 and 330 years before Christ. That means around 2100 years from now. Okay. So, and there is a lot of things like that. You see, there is several books speaking about this Tanagra painting on the right side. So this is some example, and there is a name. Of course, this is in French. So there is a name, danseuse voilée, for instance, with the edge, and there is several Tanagra, around 200. There is around 200 pottery like that in the Louvre. So what's happened? Okay, Tanagra place first, very famous, cited by Homer, the place of confrontation between Athens and the Peloponnese at 457 before Christ. This is where the Philistines gathered before the Battle of Delion at this place. So it was a famous place here, and there was a historical important place in old Athens. So for instance, this is a beautiful Tanagra statue. So the name is Woman in a Blue Coat with Fan and Sun, you see, very, very beautiful. There is another one here. And this is, for instance, a figurine of a woman trying. This is a figurine of a woman also. So this is some example of this thing. Tanagra means teenager of remarkable young woman with grace and finesse. So the first collection arrived in the Louvre in 1872, and a lot of pottery arrived at this time. Immediately after, some false pottery appears. This one is a false pottery. It's not made 2,000 years ago. And the age of this pottery it is coming just after. You know, in the Louvre, it was very popular at this time in the Louvre. Immediately after, several hundred of new Tanagra appear in the market, and it was a false. So now in the Louvre, with the thermoluminescence, they try to look at the authenticity of the different Tanagra. So they use thermoluminescence. For instance, this is a thermoluminescence profile. You see, it's coming from room temperature. So they no need to go at below room temperature. With a Rezo apparatus, it's classical to go from room temperature to 600. So this is the profile of the thermoluminescence of the Tanagra. The red signal, this is a natural thermoluminescence, red signal, and the thermoluminescence coming from the original Tanagra. This is a false Tanagra. So this is the signal of a counterfeit, this one. And you see that the Tanagra and the natural irradiation are very different. So it's impossible to have something made with raw material which are not coming from the old age, of course. That means it's a false one. So this one are from the late 19th century. And therefore have been little bit submitted to the ambient radioactivity. So this is a Tanagra response by thermoluminescence, and this is a natural thermoluminescence here, in this case. So you can see this is the frequency of the fabrication of the Tanagra about 2,500 years ago. The Tanagra was fabricated in this scale range, and a second population of Tanagra appear very close by, I think, between 200 and 300 years ago, and between 200 and 300 years ago, this was a false Tanagra, of course. So this is a statistic of all Tanagra investigated by thermoluminescence. You see, there is some are coming from this age, and there is some original, but original are still coming from almost 1,000 years. So it was famous to do some Tanagra 1,500 years ago till 3,000 years ago. I mean, during more than 10th century, they were doing Tanagra like year after year and different Tanagra. So this is 150 pieces analyzed and by thermoluminescence, for instance. So I put some advertisement of what. Of course, there is this is an uncertainty of the age because of the moisture and the evolution of the Tanagra within the age. So it's difficult to have a precise age. So there is uncertainty, which is quite big in large. You see, something like 500 years uncertainty. So, but you see, definitely we can say this one are authentic and this one are full Tanagra. So what is the methodology to do that? Of course, they have to manipulate with care without energetic light. So when they collect the statue, they have to keep it in the dark. Otherwise, we will have optical stimulation and the level will decrease. So this is, for instance, an example of bronze manipulated under red light to avoid erasing the signal when undid. So this is not so easy to manipulate. Another example, Chinese burial caravan belonging to the Tang dynasty. And again, it was important to know if it's a real one or false one. So this is an example of these two. So are they belonging to the Tang dynasty? So this is between 600 and 900 after in France, we call that Christ. After Christ, I don't know how you call that here in Japan, but in France we say 0 is before Christ and after Christ. So this Tang dynasty is about 600 to 900 after Christ. So this one was purchased in 1939, and it was important to test the age. So this is an example, for instance, of this type of pottery. So this one are the good age. But this one, for instance, is coming from was done in 1925, plus or moins 10 years after Jesus Christ, okay? So very close to the other one, but this one is not a good one. Another example, jade in China, very important in China, rock in China. And the true jade is coming from this solid solution between two natural minerals. And by trap density and thermoluminescence, you can work and can characterize the origin and if it's a real one or if it's something like it's not coming from the good place. So for instance, I would like to focus another example. in this part of close to the border of Portugal in Spain, so this is Spain on this part and the Portugal, there is on the wall a very old carving, rock carving on the wall. So they try to determine also the age of this. So when they discover this kind of carving, they were looking on the wall and they remove everything and they remove what was against the wall, and they try to look at the edge. So several techniques was used: carbon 14, mass spectroscopy, and so on. But it was very difficult to date and quite impossible. It was impossible to have a reliable age for this thing. So they tried with thermoluminescence coming from the raw material that was just with that, because besides this type of graving, there was some fragment of quartzite, and they look at the fragment of the mineral which was close to this kind of carving. So this is the datation of 3 sites in this part of Portugal and Spain. And you can see one was 30,000 years old, one was around 10,000 years old. The calcite was heated at the time of the wall decoration. So it was possible to find, besides the carving, some pottery or some stone, which give you some information about the date. So very interesting way to have information about that. But sometimes it's not working so well. This is an example of thermoluminescence datation coming from Iran, this site of Iran. And they look at the one part of pottery, you know, this is a small part of the pottery coming from this. And they try to find the edge. But you see the discrepancy is too large. You see it's between 1,000 years, 2,000 years. So this data are very dispersed, and it was impossible to have a good accuracy of this kind of this edge. So in the Louvre, it's not the only way to do thermoluminescence. I want to show you that besides the museum, there is a research lab. And this is another very strong apparatus that is beside. And the name is Accelerator Grand Louvre, Aglaé. So this is to have another technique of irradiation by high energy irradiation. And for instance, it can be used, if you look at this statue, they wanted to check the origin of the haze. So the haze from this very old Babylon goddess, 143 years before Christ. And they look at the haze, and the haze, the formula of the haze is chromium, it's a ruby. And they look at the impurities coming with the ruby. So this is particle-induced X-ray analysis, so coming from this. And they look at the signature of the impurity, and they can determine that the ruby are coming from Burma, so we call that Birmanie in France. So this is a part in Asia, and they determine the origin of the ruby from this statue in the Louvre, for instance. So
here, X means impurities
yeah,
other than chromium.
Exactly.
Right?
And they look at the impurities, and from the quantity of impurities, you can determine in which mean of which part of the world this is coming, the ruby. Of course, in the lab, the ruby, if it was artificial ruby, nobody put vanadium, titanium, iron, gallium, and so on. And I mean, it's no use to do that. So I hope that I convince you that thermoluminescence is a good tool for datation and application in datation and dosimetry. I will move very fast now in this part. Fast because I did that for most of the students in the Professor Tanabe lab, and I will show you this now. So, dosimetry also, just an information about dosimetry. Maybe you are not familiar with dosimetry, but this is the kind of application that you can find for dosimetry. It's just to control the intensity of what you receive during the exposition to high energy, for instance, or a neutron or so on. So they use this kind of dosimeter. So and this is very important for homeland security, for instance, in the airport and so on, or for environmental security.